Heidi-ho, CTM neighbor, and welcome to lesson for 10.1. We're talking about groups today here, and we've got a bunch of new terms or some review terms I hope for you down here, some things that you've seen before, but quite a few terms that we need to know to lay our foundation for knowing what groups are. And so make sure you're using those extra examples, explanations in the book as we go along. That'll help you out quite a bit, I think, with this lesson and every lesson. So let's start off by defining a couple things. We're going to have to go through a few definitions, quite a few definitions here, before we can really talk about what a group is. So let's lay the groundwork here. So here we go, laying some mathematical definitional, I think I just made that up, definition groundwork. So a mathematical system. Let's start off with that. What is a mathematical system? Mathematical system, it consists of a set of elements and at least one binary operation. So from previous chapters we should know what sets are, but you might not know what a binary operation is, so let's define that right here as well. So mathematical system consists of a set of elements and at least one binary operation, and a binary operation is this. A binary operation is an operation, or another way to say that would be a rule or operation or a rule that can be performed on two and only two elements of a set where the result is a single element. And then to put some more meat on those definitional bones, we could say a binary operation might be we're used to addition, and we're used to multiplication, things of that nature. Division, subtraction could be a couple more, but we'll just write a couple down here. So for example, that's what the EG stands for. So for example, addition, multiplication. So you're taking two elements like 1 plus 2 and you add those together and you get 3. You get a single element. We're not saying 1 plus 2 is 2 elements. We're saying an element plus an element gives you another single element. So like addition, like multiplication, like subtraction and division would do that for you too. So let's move on to this table. So make a table that looks kind of like this. For these ones down here, give a couple lines, maybe even 3 lines. You can kind of make the table as you go here. So I'm going to start off by up here writing this whole table is about. So these are some frequently used sets in mathematical systems. And I'm hoping you're familiar with all, if not all, at least most of these. We've talked about many of them already. At the time of making this video, we skipped chapter 5 for this year. We may be doing that chapter in a future year, but this is kind of a good recap, or a kind of a hashing through of the most important stuff from chapter 5 as well. So some natural numbers come first. We're going to write natural numbers. Under that, I'm leaving a little space here, natural numbers. Another way to say natural numbers is to say positive integers, because positive integers are the same thing as natural numbers. So what are the natural numbers? This was a set we learned way back in the very first lesson in our book here. It was just this set. It's the counting numbers is another way that we said that. So all the numbers from 1, 2, 3, 4, 5, skipping a single digit or skipping a single number plus 1 each time, that pattern continues on and on and on. And so as I fill this out, I'm going to be actually doing kind of a picture. So let me get that ready a second. And so I just changed the color of this, and I noticed I misspelled integers too. I forgot this E in here, so make sure you spell that correctly. But I'm going to go from this table. I just don't have enough room down here to show all this, but this should go right underneath your table right here, the picture that I'm about to draw. And I would say this should take about a half page, and this should take another half page or so, so you might have to flip over to the back. But this, I'm going to color code things here. I'm doing this first stuff, I'm going to do the natural number stuff in orange. You do not have to color code what I have right here. You might have to color code some stuff later, but this is just to help you visualize better what's going on or what goes where. So the natural numbers, I'm going to make a little box. Yeah, I could fill that in, I guess, but I'm deciding against that. So I want to have no fill, and I want to just have an orange box. I think that'll be just cleaner looking. So that right there is going to be the box that represents. I could make a circle, I could make this any shape I really wanted to, but I just think the rectangles will be most conducive to most easily representing this stuff here. So the natural numbers going in here, and just to make it easier too, I won't write the word numbers, I'll just write natural in here. So make this picture. And again, you don't have to use different colors for this, but if you want to, you're welcome to. I think it just will help it stand out. So sometimes I force you to use colors, not right now. So the natural numbers would be like this, 1, 2, 3, and this pattern would continue, so I'll put a dot, dot, dot right here. So this is kind of the least specific, or I should say the most specific rather, and I'm going to add things to outside of this. So this is the most specific set that I'm coming up with here. So it's positive integers. It's the whole numbers without zero, we're saying. So what comes next, I just kind of gave you a hint there. Whole numbers is coming next. So I'll put that next here. This is the whole numbers. And I'm going to keep using different colors, but again, you don't have to use different colors here. This is just to help you see a little easier what's what as I describe these different mathematical systems to you. Different sets within mathematical systems. So 0 through 5, and it continues. The pattern goes. The only difference between the natural numbers and the whole numbers is that the whole numbers also includes the number 0. So over here, the whole numbers completely encompasses the natural numbers, but it just has one extra one. So put another box around here, and it's completely, natural numbers are completely inside the whole numbers. The whole numbers just includes, so I'll put whole here, whole numbers just also includes the number 0. So it's 0, and then also 1, 2, 3, and so on from there. What comes after whole numbers, or what's now a little less specific, what's more inclusive, you might say. Next, I'll use the color green here for the negative integers. And actually, these are distinct sets, or they are distinct from each other. Just a second. I meant to write a little dot, dot, dot here first, and so this should be something like this, where you'd have -5, -4, -3, -2, all the way up to -1. But it doesn't go past there. It doesn't include 0. That's not a negative integer, but we have that right there. And so I just decided to change the color of that a little bit to a lighter green, and then a little less specific here is just the plain old integers. This we're actually going to draw on a picture here. So the negative integers were separate sets. They didn't have anything in common, distinct sets from the whole numbers. But integers includes pretty much everything that you see up here. It is everything that you see up here. So it would go from -5, -4, but just for the sake of simplicity, -3, -2, -1. I just don't want to write out every single possible integer, because they go on forever. So this could be represented like that. This would keep going 4, 5, 6, 7, and so on, all the way through forever and ever, infinity. There's an infinite number of integers. So within the integers is included the whole numbers, is included the natural numbers, and I will make a box here. Let's see, there we go. So this is, there we go, that's a little better, I think. So included here, I think I want to extend this out just a little ways this way, so I can include these other numbers that I had here. So I had included here the negative numbers as well, the negative, in a sense, the negative whole numbers, you might say. So this keeps going here. This is -1, -2, -3, and this pattern continues going on in this direction. So negative infinity in a sense. So let's continue our table here. So integers, negative integers is within the set of integers. This I should have written integers up here. So now all natural numbers are whole numbers. All whole numbers are also integers. And then within this set we have, after that we have rational numbers. We can get some fractions in here. So let's use blue for that. Let's go with the rational numbers. Okay, so what's a rational number? This came from chapter 5, but we had skipped that chapter for, at least for the year I'm making this video. So all numbers of the form P divided by Q, where P and Q are integers. So they come from this set of numbers right here, in other words, and Q does not equal 0. And another thing I think you should know about this is that they're decimals, representations. Always have repeating or run out of space here. I can fit this in though. Repeating or terminating digits. And so that might look initially kind of confusing, but let's come up with some examples of that. So within the rational numbers, let's make a blue box for that. Within the rational numbers, I have things of this nature. So I'm going to put all my rational numbers. I'm going to put all my rational numbers up in this area up here, and that should do it pretty well for me right there. So I'll put some examples of some rational numbers up in this area. So these are some rational numbers here. So these are all rational numbers. Everything within the blue box is a rational number. So natural numbers are rational, whole numbers are rational, integers are rational. These are some other examples of rational numbers. So 1/7, that's an integer divided by an integer. You have -2 over 11. That's an integer divided by an integer. You can have 9.16. You could write that as a fraction like this, but this is a decimal representation of that. There's something like this. You can have negative, and you can have 0 point something. We can have something like this, 580 over 3, an improper fraction is fine. We can have repeating digits like this too, and there's a lot more than this, so I'm just going to put etc. So there's an infinite number of rational numbers. There's an infinite number of natural numbers, but there's, in a sense, there's more whole numbers, there's more integers, and then there's even more rational numbers. Let's do next irrational numbers. So irrational numbers are all numbers. You look up here and it's related to this, so decimal representations cannot be written as repeating or terminating digits. So it's all numbers that cannot be written as repeating or terminating decimals. And so these ones, all rational numbers, can be written this way. These ones cannot be written this way. So these are distinct sets from each other. So this box is not going to go around the outside here because natural numbers are not irrational, they're rational. So these are two completely separate sets. So I'm going to make another box here, make it purple, but this has to be completely separate from that. And I want blue to still show up a little bit more than that. Okay, so that's good right there. So here's some examples of irrational numbers. You know some already, you may not realize it. An irrational number, an example of an irrational number could be like the square root of 2. You could have the square root of any number that is not a perfect square. So the square root of 3 would also work. Pi is probably the most famous irrational number that has its own special symbol. We also have a number like e, that's an irrational number. You could have negative square roots, something like that. There's a lot more that you could have, so I'll write etc, so we got etc. And then finally, at least for what we're talking about here, this is all we need. Real numbers is the set that has all rational and irrational numbers. So it is the set of all rational and irrational numbers. So on our picture, that means you would have a box that looks something like this, going around the outside of the whole thing. So all this stuff in the black box is a real number. So I just expanded that out just a little bit so you can see that rational, irrational, there's nothing else in here. If the number is real, it's either rational or irrational. This little gap here, there's nothing extra that actually goes in between here. There's no number that's somehow real but not rational or irrational. So this is the completion of our breakdown of what the real numbers are. So how can we be more specific? We can keep going inside here, here, and here. Are there numbers that are not included in this? Well, we have something called imaginary numbers that most of you will learn in Algebra 2. So yes, there's other things that go here, and then there's a lot of other things too. I think I've heard of something called hyperreals before. It's not included here. There's transcendentals or something like that. I've heard of things like that before. Haven't really learned too much about that myself, but there's a bunch of other numbers that we're not getting into here. A bunch of other types of sets that might be used in a mathematical system. But let's move on from there. So this, important to you, I would say, know this table. So make sure you understand this table. This is going to help us in the rest of the lesson here. We're going to be using these sets in the systems that we talk about. So another thing you need to know as kind of groundwork, foundational knowledge for this lesson for groups is to know what the commutative property is. Let me make that a little clearer there. Commutative. There we go. The commutative property. What that is and what the associative property is as well. And we're just going to talk about addition and multiplication for right now. So just put that here and here. So addition, multiplication. The addition commutative property. When I think of commuting and associating, I think of this to help me memorize or help me just remember, not necessarily memorize, but remember what's what. So this is how I keep these straight in my mind. I think of commuting back and forth to work. So I have, or to school, something like that. So A plus B, if I go back and forth, A plus B is the same as B plus A. So maybe I go from home to school, and then I go from school to home. It's the same distance. It's the same sum of miles in a sense. So A plus B, and then I just wrote it the wrong way. Equals B plus a. There we go. So this is the same as this. Multiplication, very similar. A times b equals b times a. That works going back and forth too. And then the associative property, maybe you associate with a certain group of people. So the associative property for addition looks like this. Maybe A and B want to associate with each other, and then after they associate with each other, they'll associate, or they'll add themselves to C. This is the same thing as taking A plus and then B plus C in parentheses. So B and C are associating with each other first, and then taking that and adding that to A. The associative property for addition, this is what this looks like. This is for any integers, so I feel like I should write that here. So this is for all integers, so we're talking about specifically integers right now. For all integers A, B, and C. So this has to be the case. That's what A, B, and C are standing for here. And you can do the same thing with multiplication. You can multiply A times B first and then that times C, or you can multiply B times C first and then multiply that product by A as well. And glad I checked that, because I want to make this as accurate as I can. We're saying not just for integers, but for any elements. So for all elements is the better way to write that. So make that change for all elements A, B, and C. This is a commutative property. This is the associative property. So you can, for instance, think of some numbers. You could plug in like 1 plus 3 equals 3 plus 1. 1 times 3 equals 3 times 1. You can do the same thing here. Maybe you have 2 plus 3 plus 4. You do 2 plus 3, you get 5, plus 4 is 9. If you do 3 plus 4 first, that's 7. You add that to 2, you still get 9. And the same thing works with the associative property for multiplication. So just a verbal example of each one of those. And a couple more definitions here. An infinite mathematical system is a system, or is a mathematical system where the sets of elements is an infinite system. And then, for example, we go back to what we just did here. These are all infinite systems. They go on and on forever. So natural numbers, whole numbers, integers, rational, irrational, the real numbers, all these are infinite systems. So I could list any ones of those that I want to. Integers would be an example, rational numbers, and so on. So I'll put etc. after that. So there's lots of examples of infinite mathematical systems. Most of what we talk about here in this lesson will actually be infinite mathematical systems. And a closed set, this is another foundational definition we need to know to talk about groups. A closed set, or you may hear it called as a set with closure. It's exactly what it sounds like. It's a set that is fully contained within itself, in a sense. So it's a set where a binary operation, so like we had addition, multiplication, etc., division and subtraction are different binary operations, where a binary operation performed on any two elements within the set yields an element still in the set. So a quick verbal example of that might be, take the set of integers and you add any two elements in the set. Like for instance, 2 plus negative 3. Does that yield an element that's still an integer? What's 2 plus negative 3? That's negative 1, still an integer, and you can do that with any elements in the integers. There will be some sets that are not closed sets though. And then we're doing one more definition here, and then a little table, so I'll go on, move on to this. So we need to know one more thing here is what an identity element is. So an identity element, and if you think of something that has a certain identity, like you have your identity, somebody else has their identity, and an identity element will be something that we add or multiply by that doesn't change the identity of the number you started with. So that is basically what we have. This is what I just said in a more formal definition way. So identity element is an element in a set such that when a binary operation is performed on it, and any given element in the set the result is the given element you started with. So let's put some meat on this definition's bones here, and let's make this a little more practical, a little more understandable, I think. So for integers, let's talk about the set of integers. For integers, the additive identity, so talking about addition here, the additive identity, what's a number that you can add to any number in the integers that doesn't change the number itself? Well, that would be 0. So the additive identity is 0. And we could say that since you take any number, we'll call it any number A. You add A plus 0, that's the same thing as 0 plus A, which is the same thing as just A, what you started with. And the multiplicative identity is 1. You multiply 1 by any number in the integers, and you're still going to get that same number you started with. So the multiplicative identity is 1. Since, take any old number, A, you multiply by 1, it's the same as 1 times that any old number, and you get A. So you get what you started with, basically. With the identities, you always get back to what you started with. And then one other definition here, and then we can finally talk about what a group is. So an inverse of an element is the element that yields the identity for the specified binary operation. And so you might say, I don't really understand that, so let me give you an example of, a couple examples of that real quick. So for example, 2 plus what's going to get you back to the additive identity. If I'm adding things, 2 plus what equals 0? 2 plus negative 2 equals 0. So this, now I'm talking about, this would be the set of integers, but I won't write that down here. 2 plus negative 2 is 0, so negative 2 is the additive inverse. In a sense, it undoes 2. It gets you back to the identity. It gets you back to 0. So it's the additive inverse of 2. And you could also say, to do a multiplicative inverse example, you could say 3 times 1/3, the reciprocal of 3, gets you to 1, gets you to the multiplicative identity. So 1/3 is the multiplicative inverse of 3. So now we can finally talk about what groups are. So that's the title of this lesson. That's the big thing to know for this lesson. What are groups? And so we're going to start off here with the properties of a group. To define what a group is, we have to say what the properties are of it. So any mathematical system that meets the following 4 requirements is called a group. There it is. So we finally have a definition of a group once we list the 4 requirements. So it's called a group for a given operation. So we might be saying the operation is addition, or the operation is multiplication or division or something like that. So it's called a group for a given operation. So here's requirement number 1. It has to have, or the set must be closed. So the set is closed. That's requirement number 1. Requirement number 2, it has to have an identity element. So it has an identity elements. Requirement 3 is that every element, not just one, but every one, has an inverse. Every element has an inverse. And then requirement 4, that the set has to be, or the set is, associative. And then I'm going to put kind of a little line here. So this is true of a group, and then there's a more specific type of group that still goes along with this. So if rather than saying it, whoops, I should say if a system meets the following 5th requirement, it's also called a commutative or you may hear it called an abelian group. They mean the same thing. So a commutative or abelian group. So this is commutative group now, or abelian group is another way to say that. Group for a given operation. And so number 5 is that, well, if it's a commutative group, it should be commutative. And so if you said that, you got that right. So the set is also commutative. And so these guys over here, these are some pretty famous people dealing with groups and whatnot. This is Niels Abel, and then this is Everest Galois. I gotta look up his name, how to spell it. So it is Galois. You don't have to remember these names, but just a little background. This guy was a Norwegian. This guy was French, and both of these guys, they died pretty young. This guy died at 26. This guy died at 20. But they both, in their short lives, were able to kind of help develop group theory, you might say, and kind of started the basis for a lot of what we have kind of compiled throughout the last few hundred years today. So these guys were around in the 1800s, early 1800s, were both of them. Gawa, actually, if you watch the first episode of Numbers, the show, you can learn there, and you can learn on page 564 more about these guys, so page 564 if you want. But he died in a duel, and so the night before he was involved in this duel, he wrote down a bunch of his work and tried to basically put it in a form where somebody could use it. And so they found his work later, and a lot of group theory, got a lot of group knowledge in a mathematical sense came from some of the beginnings of it came from what he did. So pretty cool story. Not cool that he died so young at 20 years old, but even in youth you can do something that could change the world. So is the set of positive integers, we're finally doing some examples here, is a set of positive integers a group under the operation of multiplication? So how can I tell if something's a group? So go back to what we just said here. We need to check all four of these things, and we're just going to go in order with each one. So step 1, check if step 1 works. If it does, then check step 2. If that works, check step 3. If that works, check step 4. If they all work, then you have a group. So let's just go one at a time here. So let's check step 1. Does this work? If you have, step 1 is to check if the set is closed. So let's underline these things. So it's closed, identity element, has an inverse, set is associative, and the set is commutative. So to check if it's a group, we got to check these 4. To check if it's a commutative or abelian group, we got to check all 5. So let's check if the set is closed. So you take a positive integer and you add that to another positive integer. Do you get a positive integer still? So like 1 plus 3 is 4. Can you think of anything that doesn't work? You think about it, and you think about it, and there's nothing that's not going to work. So we could say any positive integer. I'll put a little check mark. That one's good to go. Any positive integer. This is under multiplication, so multiplied with another positive integer is always a positive integer. So it's closed. All the positive integers multiplied by each other would still give more positive integers. It wouldn't be suddenly a negative integer, and positive times a positive always will yield a positive integer. So let's check step 2. Is or does the set have, does the system, the set, does it have an identity element? So can you multiply something by each integer, each positive integer, and still get that same positive integer? And if you think that through, you could say yes you can, because 1 is that element. So 1 is a positive integer, and 1 times any positive integer is still the same positive integer. So basically you're trying to come up with a counterexample. If you can't come up with a counterexample, then it works. But sometimes there's sneaky counterexamples. So let's check step 3. Step 3 is saying every element has an inverse. So the multiplicative inverse is supposed to be 1. So think of a number, any positive integer, like let's say 4. So what's 4 times something? What times 4 gives you 1? 4 times 1/4 would give you 1. Is 1/4 a positive integer? No, it's not. So you would say no here. So we just verbally came up with a counterexample. If you can come up with a counterexample for any of these steps, then that step is not going to work. So let's write down what I just said there. 4 times 1/4 equals 1. 1 is the multiplicative identity, and so this is the inverse of 4. So this is the same. So 4 times 1/4 equals 1. So 1/4 is the multiplicative inverse of 4, but it's not a positive integer. I think maybe a little clearer way to say that rather than it's would be to say but 1/4 is not a positive integer. Everything has to be a positive integer here within this for that to be true. So every element has an inverse. So this has an inverse, but it's not in the set of positive integers. So this one we say no, and so we can say therefore it, by saying it, I'm saying the positive integers under the operation of multiplication. So it's not a group. Do we need to check step 4? Well, if step 3 didn't work, there's no need to check step 4. So we'll write that underneath here. There's no need to check step 4 since step 3 didn't work. And so let's do one more example like this, just so that hopefully you'll have it down a little better. So let's say this is the set of integers, a commutative group. So now we gotta check all 5 things over there. So is the set of integers a commutative group? Under the operation of addition. So notice this time there's a difference here. I have integers instead of just positive integers. So I'm talking about all integers. I'm talking about 0 as well. 0 is an integer. And so I've got more things to choose from, you might say, in a sense. So I got to check all 5 steps now. So just go in order, and let's check first. Step 1 is the system, or is the set closed. And so is it closed? If you take any integer plus another integer, we're doing addition here now, do you get still another integer? And this you could check all day if you wanted. You'd say, yeah, this is going to be true. So any integer plus another integer is still an integer. There is no counterexample to that. So step 2, let's check that now. So step 2, we want to check and see if it has an identity element. So is there something within the set of integers that you can add to any integer that still gets you that same integer that you started with? And yes, there is, because you can use 0. So we can take 0, this would be our explanation for this step, 0 plus any integer is still the same integer. Step 3, we need to check if there is an inverse for every element. So let's do that. Whoa, didn't want to go there yet. I'll pretend you didn't see that. That's right. And so is there an inverse for every element? So you take, let's think of positive integers first. So any positive integer, put a check mark here. So you're thinking, yeah, there is. Well, let's explain that. Why is that true for all the elements here? So any positive integer has its negative as its additive inverse. And vice versa. So what do I mean by that? I mean something like this. I can take 5 plus negative 5. That's an integer and it's negative. That gives me 0. That gives me my additive identity. You could also say something like negative 8 plus, it's negative in a sense. The negative of a negative is a positive, so it's also 0 there. So this works with any integer you can think of, positive or negative. You take the opposite of it and it gives you 0 added together. And we also need to check 0 too, or 0 as well. Might be a better way to say that, so you don't think I'm saying 0 and then the number 2. And so we have this and 0 plus, does 0 have an added inverse? Can you add something to 0 and still get 0? Yeah, you can add 0 to 0 and still get 0. So you would say 0 is its own additive inverse. Okay, step 4 now. Is it associative? So can we, in other words, can we put A plus B together and then add C? And then is that the same thing as A plus and then B plus C in parentheses first? So we think that through. I would say yes, that's definitely going to work out. And we could say for any integers A, B, and C, it's always going to be true that A plus B first and then plus C is the same thing as A hanging out by itself first, added to B plus C coming before that, coming before adding A to it. So that's the case. That's going to work. Any integers, 3 integers you plug in here, it's always going to work out like that. And then step 5, I'm thinking maybe we just got one more. Maybe this one's going to actually work. And so is this going to work? If you take A times B, any 2 integers, and multiply them together, you get the same thing as B times A. Does the commutative property work? It does. So this, for any integers A and B, it's the case that A times B equals B times A. Doesn't matter what 2 integers you come up with, that's always going to be true. You can even plug in 0 and that's still going to work. So is this a group? Yes, yes it is. So you'd say therefore it is not just a group but a commutative group, because that's what we wanted to check first of all. So is it a commutative group? Yes it is. And then one little side note we'll make on this one for step 5 here. When do you need to check step 5? It's only if you're checking if it's actually a commutative or abelian group. So let's write that down as well off to the side here. We only need to check step 5 if we're trying to tell if it's commutative. So if I was just asked here for this one, is it a group and not a commutative group, I would have stopped at step 4. I could have said yes, it's a group, but since it asked if it was a commutative group, I also needed to check step 5. And then just kind of a fun little thing to end the lesson here, there's something called the enormous theorem. You can look up on page 565 about that. Just going to read that real quick to you, what it says here. Mathematicians are attempting to make the world's longest proof shorter. It's called the enormous theorem. More than 100 mathematicians toiled for more than 30 years to produce a proof known formally as the classification of finite simple groups. Completed in the 1980s, it consists of some 500 publications totaling 15,000 pages. So this is a 15,000 page proof. The theorem established that all finite simple groups can fall into 17 infinite families or 26 so-called sporadic forms, and it goes on. And here online I found somebody that made a timeline of the theorem, so some of this background work, and then they started proving things, the different types of families or sporadic forms, and there's actually been some more work more recently on this too, so even going down to 2000 and 4. Somebody even came up with some pretty weird names. If you look at some of these, the baby monster group, that's what I was most intrigued by. There's a baby monster group. Very, very interesting. Yes, this stuff is pretty fascinating. So hopefully you found what we did there helpful, and let me know if you have any questions in class.